Find the angle between the planes x plus y plus z is equal to 1 and x minus 2y plus 3z is equal to 1, and then find the line of intersection. So to find the angle between the two planes, we're going to use our definition of the dot product. So you could check out my video about the dot product, which will be in the top right corner. But what we covered in that video is that the dot product of two vectors, a and b, is going to be equal to the magnitude of vector a times the magnitude of vector b times cosine theta. So if we rearrange this expression to just give us in terms of theta, we'll have theta is equal to, we'll have the cosine inverse of the dot product of a and b divided by the magnitudes of both a and b. So now that we know what we're looking for, let's find our two vectors, a and b. So we'll call our vector a, we'll call that the normal vector of our first plane. And to get the normal vector, we just look at the coefficients of our plane function. So for our first plane, plane 1, our normal vector is going to be 1, 1, and 1, because all of those don't have any coefficients. And then for our vector b, that's just going to be the normal vector of our second plane. And we can see that our coefficients are going to be 1, -2, and 3. And now let's just find our magnitudes for each of these. So the square root of 1 plus 1 plus 1 is going to be equal to the square root of 3. And then 1 squared plus 2 squared plus 3 squared, well, that's going to equal to 5 plus 9, and that's equal to the square root of 14. And then lastly, let's just take our dot product of our two vectors. So we'll have 1, 1, 1 dotted with 1, -2, 3. And let's just write that out. So we'll have 1 times 1 plus 1 times -2 plus 1 times 3. That'll be 1 minus 2 plus 3, which is equal to 2. So now that we have the magnitude of a, our magnitude of b, and then our dot product, we can just plug it into our expression for theta and see what our angle is going to be between the two planes. So we'll have theta is equal to cosine inverse of 2 over the square root of 3 times the square root of 14. And then my professor always said it was fine to leave it in the exact form. But if we were to simplify this, put it into our calculators, we would receive 72.025 degrees. So now for part B, we need to find the line of intersection between our two planes. So to start that, we're going to need our normal vectors of our first plane and our second plane. So our first one was 1, 1, 1, and our second one was 1, -2, 3. And what we need to do is take the cross product. So if we have our first plane up here, let's say plane 1, and then our second plane down here, plane 2, we learned in our first part that they have an angle between them of around 72 degrees. What our cross product is going to do is it's going to find some vector, the normal vector, that represents this line right here. So let's do that. If we take our cross product, we'll have I, j, k up in the top section. We'll have our first plane, 1, 1, 1, and then our second, 1, -2, 3. If we take our cross product, we're going to have 1 times 3 minus -2 times 1, I, minus 1 times 3 minus 1 times 1, j, plus 1 times negative 2 minus 1 times 1, k. So simplifying everything, we'll have this negative will become a positive, so it's going to be 3 plus 2, which is 5i, minus 3 minus 1 is just 2, j, plus negative 2 minus 1 is just negative 3, so negative 3k. And then if we write out our normal, let's call it normal 3, just for clarification purposes, we'll have 5, 2, or negative 2, negative 3. So now that we have our normal vector for that line, for that green line, we need to find 2 points on both of our planes where they intersect. So let's write out our equations for our planes again. We'll have x plus y plus z is equal to 1, and then x minus 2y plus 3z is equal to 1. So let's say let our z equal to 0 for both of these. So if we perform that action, we'll have x plus y is equal to 1, x minus 2y is equal to 1. And now we can see that this is just a system of equations. So if we go to solve for x, we would multiply the top one by 2 and subtract both of those. So if we do that, we'll have 2x plus 2y is equal to 2, minus x minus 2y is equal to 1. And as you can see, our plus 2y and our negative 2y will reduce. They will simplify. And we're left with 2x minus x, which is equal to x, is equal to 2 minus 1, which is equal to 1. So let's take one of our functions. Let's take our x plus y. We'll put our x is equal to 1 back into there. So we'll have 1 plus y is equal to 1. Subtracting 1 from both sides, we'll have y is equal to 0. And so what that means is a point of intersection on our line for both of these planes is going to be 1, 0, 0. So we have all of the information now that we need to find a line of intersection. So the only key parts that we need to make our equation of our line is going to be our point on a line and then the normal vector. So to make the equation of our line, we just follow this expression. We have x is equal to our x naught plus at, our y is equal to y naught plus b of t, and then our z is equal to z naught plus c times t. So what are the points x naught, y naught, z naught, and a, b, and c? So if we look at our point of intersection on our line, that's going to be our x naught, y naught, and z naught. So x naught, y naught, z naught. And then for a, b, and c, that's just going to be from our normal vector. So a, b, and c. So if we just plug those into our equation for our line, we'll have x is equal to 1 plus 5t, y is equal to 0 minus 2t, and z is equal to 0 minus 3t. So then when we write out our parametrized function of a line, we can just write out 1 plus 5t, negative 2t, negative 3t. And that's our equation of our line.